Okay, so we just saw Pauli's argument that it's impossible to have a self-adjoint time operator that is canonically conjugate to the Hamiltonian. So what else can you do? After all, we just want to describe those detectors. Now, the first realization that helps here is that so time and actually arrival time, that's the thing we want to measure. There's no sensible measurement of time as such. I don't know what that would be. I mean, also for the classical particle, you register the time of certain events. So it's the same here. In the quantum case, arrival time should be given by, let us say, a generalized observable. And POVMs is another way to say that in the jargon, and that means for every interval, of the time axis, right? Let's say of the time axis, give a positive operator. Let me just call it F pertaining to that interval, right? So, this is an operator on the Hilbert space of the system. It should be positive, right? And so F is additive over intervals, right? So additive over intervals, that is, it's a measure. I won't bore you with the technicalities. And of course, the probability that some time happens should be less than one. Right? So actually, we allow here. Sometimes it's useful to allow the possibility, um, that particle isn't ever detected. So if I have some detector somewhere, this probability will be the expectation value of f will the probability that the particle is detected at all. So the trace with a density operator that describes the preparation of this operator. So that's the interpretation now, right? So that is the probability for arrival in that interval. Okay, very straightforward. It doesn't have to be a projection operator. This is the thing that Pauli didn't have in mind, right? So his notion of observable was more narrow, and that's why I said generalized. So it doesn't have to be a projection, and if you use that generalization, which is anyhow completely commonplace in quantum information theory, and so it's definitely just an equally good description of probabilities coming out of quantum systems, then that's the first thing that you do. Now, Pauli's commutation condition can be phrased in this language as covariance. And by that I mean that if I apply the time evolution to this operator, right? So I take, maybe I let me abbreviate the time evolution operator as this. And then if I apply that in the Heisenberg picture to this operator, then this is just the corresponding thing for a shifted interval. plus T1 plus T, T2 plus T. Another way to say that is if you want a Schrödinger picture statement, if I shift the preparation in time, then the whole arrival time distribution will shift by the same amount, right? In this way. So that's equivalent. So this is basically for a projection valued measurement. This would just translate to the corresponding to this kind of statement about the spectral family of the operator T. We don't have this operator, but this has a direct interpretation anyway, and that's what we use. Right? So this is the covariance condition for arrival time measurements. So basically, this is like approach number one to arrival time. Right? So, and this is actually in several papers. So people who did that early on is Klioski. We have Ludwig was thinking along those lines, and Euler were early proponents of such a notion of covariant arrival time. Okay, this is one thing to note here is that this covariance condition depends on the whole Hamiltonian, and so on the dynamics. So now if you want to discuss situations, for example, take a tunnel, right? So you have a tunneling potential, particles are coming from one side, and they hit some barrier. And then you ask, when do they come out? But that's actually a frequently discussed question. Then this covariant approach tells you that you have to find something, some operator valued measure that is covariant for this complicated time evolution. But what you really want to say is that we take the same detector and put it after the tunnel, and compare that with a situation where the dynamics is actually different. Right? So you want to say the same detector in another dynamical environment. So how would you say that? And so actually this is one of the problems with the covariant approach. It depends on the whole dynamics, and it's difficult to build good models with it. So let me give you another approach, and I'll talk about the relation between the two later, that does this in a very flexible way, in a very useful way. And so that is my next screen. So the next approach I want to describe to you is what I call absorptive arrival times. And so the idea here is that you modify the dynamics by an absorbing term. So actually, sometimes this is called an optical potential. Don't ask me why, but so the result is that you have something like, so the Hamiltonian gets replaced by an operator K that sort of plays the same role, but it's not emission. It's my old Hamiltonian. And I have another term where M is a positive operator. That's at least one way to do it. And then if I look at the time evolution operator, then e to the minus I t k over h bar. I do the same thing as before, only I take the k. Right? This will be something like e to the minus I t h, and then minus t m. Now, since m is positive, this tends to be smaller than 1. And actually, the way to show this, that this is actually an operator. So this is, let's call this maybe Vt. The other one was Ut. So then actually the norm of Vt is less than 1. So it is still an exponential, so it is a semigroup of operators, but it consists of contractions. That it just means it's operators with norm less than 1, so it's a contraction semigroup. Right? So now, I mean, why do we have unitarity in quantum mechanics? We have unitarity because there's a preservation of probability. And this has changed now because the particle may arrive and sort of be no longer be part of the game. So the particles that have arrived are taken out of the system, but the rest is happily moving on. Right? So this is a description that describes the dynamics only of those particles that are still around and haven't arrived. Right? So then, with this interpretation, it's pretty clear that the probability for arrival um, in the time interval t1, t2 is the difference. So let's say starting from pure state is the norm of the operator at the earlier time of the vector. Sorry. Right, so this number is smaller because that's a later time, so it's further contracted. So that is this you can write as the expectation value of an operator f that is exactly like one of these positive operators. Right? So that describes the probabilities. And this is now the operator that I was talking about earlier. Right? It's still an operator valued measure. And it's now defined only for T1 and T2 positives. At some point, you turn on, in time zero, let's say, you turn on this operator M, and it starts absorbing, and the absorption probability just describes how many particles have arrived. Right? So this is the absorptive approach to arrival times. Now I have to, just on the technical side, I have to add this way of making an operator, the generator of a contraction semigroup, is a bit special. Right? So often it's just not an operator, but it can be very singular perturbation. We'll come to that when we discuss arrival at a point or arrival at a boundary. Then it's actually this way. You can't really identify this operator, but there's still a good way of doing this. Okay, so this is the absorptive approach. So let me also come to the third. So this is so let me come to an even finer description of arrival times. So let us consider a third type of arrival time measurements that you can do. I call these interactive. And those are simply the indirect measurements. I mean, there are many contexts in quantum mechanics where you do that. You measure something indirectly, which means that you couple your system to a probe system, and then you measure something on the probe, right? So here's your system. You have some interaction with a probe that you have somehow prepared, right? And here you measure time. And then maybe the system will go on and you can discuss what happens to that, right? So that frequently happens. And now you can, of course, so this is just a general interaction, right? So and we know how to describe an interaction in quantum mechanics, so there's nothing mysterious about this. It has to be said, though, that this is a royal pain to do in practice. Right? So if you have a concrete interaction and you want to describe that kind of indirect measurement, this can be very complicated, and so it's rarely done. You would do it when your experimental setup requires a very precise modeling. Then you would go to this extreme. Also, you have to say how you measure the time there, but then take one of the other approaches. It doesn't really matter so much. The main thing is that you have a concrete model of how the interaction works and therefore how the time is extracted. For example, you might be interested in an ionizing detector, like in a Geiger counter. Right? So what do? Your system hits an atom and it ionizes the atom. So then you measure something on the ionized an electron that comes out of the atom. And this would then be sort of a measurement of the ionization time. Right? So for that, you could take a time observable covariant with respect to the free time evolution, something like that. But in any case, working like this is a measure that you would only go to in practice when really you want an extremely precise modeling of a particular experimental situation. It doesn't completely solve this problem of arrival times, even if you could do that, because you still have to measure on the probe, and you need some notion of how to measure on the probe. Of course, you can iterate that process, but that's even worse, right? So in practice, probably you would use some of the other ones to ground this whole thing and actually make a time measurement out of that. So I will tell the other models. So there's the covariant model, or the covariant approach to arrival times. There's the absorptive. The absorptive sort of takes some part of the back reaction of the detector into account and does it in a fairly systematic way, and also in a way that can be modeled well. So of course, arrival means arrival somewhere, that is at a detector. Right? So the detector is somewhere, so the operator M in the arrival observable, or in the arrival dynamics, that will be somewhere in space, typically. Right? So there you can actually build up complicated detector situations with some confidence, like how the localization of the detector is brought into your theory. In the covariant approach, this is not so clear, right? And therefore, I think the typical thing that one should do is actually a combination of the absorptive with the covariant, and I'll tell you how to make the connection between those. So my plan for the further lectures is that I first give you a general theory of the covariant arrival times. There is some mathematical stuff that one can say about that, including, for example, uncertainty relations for time and energy in this case. Then for the absorptive case, there's also some general remarks that have to be made. In particular, describing how we get this combination of arrival time and arrival place, like which detector has clicked. That's something that you also want to know. Right? And there's a clear way of doing that in the absorptive case. Then I'll describe how they're related. Actually, one clear indication here is that the absorptive arrival time will start at time zero. Right? So you turn on the absorption at some point, and this is a semi-group. It doesn't make sense if you extrapolate for negative times, it will increase the normalization sometimes. And that makes no sense at all. Right? So it really is intrinsically works from that time onwards where you've turned on the detector. Now, if this is a good detector, it actually won't disturb the dynamics of your particle very much if it had already been on a bit longer. So you expect actually the limit to exist for shifting this time to minus infinity. And it turns out that this is basically just scattering theory. So from that, you get, again, a covariant arrival time. So this is the connection between the absorptive and the covariant approach, shifting the beginning time of the absorptive measurement to minus infinity, which makes sense in situations where you could actually talk about a detector sensibly. Then you would get a covariant approach, but you also get a particular one, right? So you have to solve the scattering theory, and from that you get then a covariant time measurement, of which you can say, well, this describes a certain battery of detectors that you previously put into your modeling. I will not discuss the interactive arrival times anymore. This is something that, as I said, is a last resort and only used for very, very detailed modeling.